We all know that matter can be in a solid, liquid or gas state. But there are actually several other states of matter, and superconductivity is one of them. Superconductivity has two very interesting and remarkable properties that cross over into the quantum mechanic world of atoms, thereby breaking with traditional physics, through which we normally understand materials. They allow electrons to move without any resistance, and they establish magnetic fields that can carry up to 50,000 times their own weight. Welcome to Superconducting Superconductors. The phenomenon of superconductivity was discovered in 1911 by Kamerlingh in Leiden in Holland, when he managed to cool down mercury to approximately minus 270 degrees. At this temperature, the material becomes superconducting, and zero resistance was observed for the first time when a current was sent through it. That is to say, there was absolutely no loss, and the current flowed freely through the mercury. Let me demonstrate some of the almost magical properties of superconductors. Here we have a superconductor comprised of yttrium, barium, copper and oxygen. And here, an ordinary magnet. No interaction. They pay no attention to each other. But look what happens when we cool the superconductor down to minus 200 degrees. Now the magnet repels the superconductor. But look now what happens if I gently press the magnet onto the superconductor. Now they are attracted to each other, and the magnet floats on top of the superconductor. This phenomenon, where two magnetic fields cancel each other out in the superconducting state, is called the Meissner Effect. We'll return to that later. It's a purely quantum mechanical effect that gives rise to this incredible anti-gravity. The principles we know from the atomic level, namely quantum mechanics, are now valid for tangible materials. I can rotate the magnet without any resistance, as you can see here. What we saw here builds on two properties of superconductors. One, they can conduct substantial electric current without resistance. And two, they repel any magnetic field from within, the so-called Meissner Effect. Electric currents can be understood metaphorically as water flowing through a garden hose. The water flows away. In the same way, electrons can flow through a wire. But they bump into each other and into the atoms of the wire, thereby losing energy, and the material gets hot. And when the resistance and energy loss that the electrons are subjected to on their way through the material ceases, we're talking about superconductors. They're in a brand new state of matter, where the electron current flows entirely without resistance. In order to understand the Meissner Effect, that is, that the magnetic field is cancelled from the interior of the superconductor, we need to remind ourselves what a magnetic field actually is. If you sprinkle metal dust around a material and then make it magnetic, the metal dust will accumulate in very specific patterns corresponding to the magnet's magnetic field. We call these patterns or lines magnetic field lines. When we attempted to push the magnet closer to the superconductor, it immediately produced some electric supercurrents on its surface, which generated a corresponding magnetic field in its interior. This occurs because a superconductor cannot tolerate a magnetic field penetrating through its mass, as opposed to non-superconducting materials, which a magnetic field can freely pass through. But when the magnet is forced down towards the superconductor, some of the magnetic field lines are nevertheless forced down through the superconductor as well. The field lines are then locked in the superconductor, thereby linking the magnet to the superconductor. Here's a superconductor, identical to this one, except wrapped up so it stays cold. I can place it on this magnetic track, and a frictionless and completely free movement of the superconductor is now possible, like this. As long as the magnetic field experienced by the superconductor does not change, it's happy and it remains on the track. Due to major changes in the magnetic field on the outer side of the track, the superconductor is held in place and doesn't fall over the edge. But what is really happening when we dive down into the superconductor and take a look at what's behind the Meissner effect and the zero resistance? What is their atomic origin? There are only two fundamentally different particles in nature, fermions and bosons. Fermions are egocentrics who prefer to live alone with minimal contact to their peers. Bosons are very social and like to be with the others and do the same thing as the others. A material's electric and magnetic properties are controlled by the electrons in the material, and electrons are fermions. Fermions, or electrons, cannot generate a superconducting state when they are on their own. But inside the materials, where there are almost an infinite number of electrons, they can sometimes be persuaded to form pairs. This is precisely what happens in a superconductor. The electrons form pairs and become bosons. And now they can all join together, because bosons like to be together in one large macroscopic quantum state. In other words, the electrons are now dancing the same quantum mechanical dance, and thereby completely altering the properties of the material, making it superconducting. But how do electrons actually join together? They usually repel one another. To understand this, we need to remember that they live in a material with many other large atoms with positive charge. So when an electron in a material passes by the heavier and positive atoms, it has an attractive force that draws the atoms closer. The atoms only move back to their equilibrium position slowly. This leaves a period of time where another electron is attracted by the excess amount of positive charge that is found locally there. Thus, it is through the slow movement of the positive atoms that the electrons effectively feel an attraction to each other. In recent years, however, we have discovered completely new superconductors, the so-called high-temperature superconductors, and are once again faced with amazing mysteries. In fact, it could be said that understanding high-temperature superconductors is one of the biggest open questions in modern physics. The mechanisms that make them superconducting remains a great mystery. One of the new mysteries about high-temperature superconductors concerns their very powerful electron repulsion, meaning that materials that are normally very poor electric conductors, and thereby used as insulating materials, suddenly can acquire superconducting properties. It's actually so strong that the electrons cannot move away from each other and thus remain frozen to certain atoms. It's a real mystery as to why such materials are the best superconductors. And perhaps this is a case of brand new ways of quantum operations that we have to understand before we can predict new materials that are superconducting at even higher temperatures, and thereby increasing their applicability. For example, today there are levitating trains in China and Japan making use of superconducting effects and their colossal load capacity. But superconducting superconductors are also used in many other places. For example, they're used in MRI scanners in hospitals, in particle accelerators, and in laboratories around the world where you need large magnetic fields. The frictionless rotation has also been used in powerful marine engines. But the potential is much greater, and the dreams as well. Today, up to 20% of all electricity produced by power plants is lost on its way to the consumers. But with superconductors, which transport current with zero resistance, this loss will be zero. The same principle could also be used to store energy. Excess energy, which is currently lost, could be transferred to large current-carrying batteries, which, again because of the zero resistance, can store the energy for an infinite amount of time. Quantum levitation has also prompted people to dream of new technologies and a society with levitating cars and super-fast transportation between the world's major cities. But true of all current superconductors is that they require cooling, and thus use a lot of energy for this purpose alone. If we manage to find materials that can act as superconductors at even higher temperatures, this will be a revolutionary breakthrough. Perhaps it'll even be the beginning of a new era.